Good morning. We're going to talk about non-silicates today. And these include halides and salts. And in this case, the anion is chlorine minus, in some cases fluorine minus, or bromine minus. And they include simple halides such as halide, NaCl, or Sulfide, KCl, and potassium bromide and fluoride, CaF2. These tend to be minerals with isometric or cubic sort of crystal structures. They're brittle, perfect cleavage, and they tend to be dissolve in water. The next group we're going to talk about are the oxide and hydroxide minerals. Oxide minerals, the anion is O2 minus, just like in silicates, and hydroxides include an OH group, OH, which has a -1 charge. Okay, the oxides include simple oxides like TiO2, rutile, which is hexagonal, important titanium mineral, SnO2, the chief ore cassiterite of tin, and also spinels. And the general formula for spinel is AB2O4, spinel, and that includes the mineral spinel, MgAl2O4, and Fe2, Fe3 taken twice, O4, which is magnetite. The most important and strongly magnetic iron mineral. So in this case, magnetite has both iron 2+ and 3+. If the iron is completely oxidized, the stable oxide is hematite, which is Fe3+ taken twice, O3, hematite. Famous banded iron formations, early oxidation of Earth contain these. And the analogous mineral for titanium mineral is FeTiO3, ilmenite. Okay, these are all important oxide minerals that occur in the crust and upper mantle. In addition, near the surface where there's plenty of water, we get hydroxide minerals. So the analogy for hematite in the hydroxide minerals is FeO, this is a 3+ iron, OH. Includes an oxygen anion and an OH. This is goethite and several other polymorphs. And there are numerous ones, including aluminum hydroxides, like this, AlO, OH, for example. Okay, now we're going to go on to the next class of minerals, and these are sulfide minerals. And sulfides, the anion is S2-. And they form stable compounds with transition elements. And they are formed typically by hydrothermal means. And these are relatively soft, metallic or semi-metallic compounds and have high electrical conductivity. Okay, and they include many of the ore minerals, PBS or lead sulfide, that's galena, zinc sulfide, that's sphalerite, the main zinc ore, CuFeS2 or chalcopyrite, the chief copper ore, and two important iron sulfide minerals, FeS2, pyrite, or fool's gold, and Fe1-X S, that's pyrrhotite, which is slightly magnetic, okay? the only slightly magnetic sulfide that's common. Okay, so these form is as commonly simple cubic forms and with soft structure. Okay, now they're only stable in the Earth's crust where there's not much oxygen. And where there's oxygen near the surface of the Earth, sulfur 2-, if you add 2 oxygens like this, it produces sulfate 2-, and that leads us to the next class of minerals. Okay, so the final class are oxide compounds with small cations. Okay, and one of those would be sulfate, SO4 2-, where sulfur is +6 charged. Another one is CO3 2-, that's a carbon 4+. In addition, there is PO4 3-, the phosphate group. And then there's the tungstate group 2-, and the molybdate group 2-. Okay, and phosphorus is +5, tungsten is +6, molybdenum is +6, and then a similar compound, the borate group, or BO3 3-, and this is a 3+ cation. Okay, so these oxide compounds are extremely stable, and they produce a number of very common stable minerals, and they act as a unit. So we would write them as Ca and then SO4. That's the sulfate group. That's anhydrite. Barite is another common one. Carbonate groups, which include calcite, CaCO3, calcite, which fizzes an acid, and CaMgCO3, that's dolomite. Okay, and then phosphate, a common one is apatite that forms your teeth, Ca5, PO4 3 times, and then an OH, F, or Cl. Okay, apatite. The good one is the fluoroapatite. That makes your teeth very strong. So we write the formulas of these with this group intact because most cases, except boring, these are what are called anisodesmic compounds. And that means that the bonds between the small cation and the anions are stronger than the bonds between the anion, oxygen, and the calcium. So, for example, if we pick carbon, the carbon cation is like that. It's +4, right? Carbon +4. And it's surrounded in triangular coordination by 3 oxygens. So that means we can calculate the bond strength by Pauling's rules. The bond strength is equal to the charge of the cation +4 divided by its coordination number. 1, 2, 3 is the coordination. It's equal to 1.33. That means that 2/3 of the strength of the oxygen 2-, so 2/3 of the bond is with carbon. And the other 1/3 is with, for example, a bond is with calcium. So this is a weak bond, and that's a strong one. So we write those groups as a CO3 group because it sticks together. And these form these anisodesmic compounds. The compound itself acts as a giant anion, and it's stable together. Okay? Thanks.